All right, in this video we're going to be discussing parallel circuits. So what is a parallel circuit? Well, a parallel circuit is a circuit that has more than one path for current to flow. So we can have multiple legs or branches with multiple loads, and each load being able to operate kind of like in its own circuit. So a little different characteristics from a series circuit. What happens on one leg of a parallel circuit does not affect what happens on the other legs of a parallel circuit. So we're going to build a parallel circuit on the table, and we're going to talk about some of the characteristics and laws for a parallel circuit. All right, so our parallel circuit is going to be a little bit different than our series circuit. So with our parallel circuit, what I'm going to do is I'm going to hook the power side of each one of these three loads together. So I'm just going to piggyback and hook all of the power sides together. So that now I have voltage from my power supply at each one of these legs. There's nothing in between the voltage power supply and each one of these legs that could possibly eat up any of the voltage, okay? So remember, voltage is used by resistance. The resistance in this circuit is gonna be each one of these light bulbs. All right, so now that I've got all the power sides hooked together, what I'm gonna do is I'm gonna hook the ground sides together. I've got all the power sides hooked together. I've got all the ground sides hooked together. Now I just need to connect this ground path back over here to my power supply, and my circuit should come on. The first thing we notice about the parallel circuit compared to the series circuit is with multiple bulbs in the parallel circuit, they are all very bright. Each one of these bulbs in a parallel circuit is getting the full source voltage, because each one of these legs of the parallel circuit acts like its own circuit. So if I start to unplug these, then this leg is still able to operate because it has power coming from the power supply through the load back to the ground. When I hook the second one up, it still continues to work. So let's take a look at the voltage drop in a parallel circuit. So remember, voltage drop is the amount of voltage used. So in a series circuit, they had to share their voltage. In a parallel circuit, they should get source voltage. So let's see what that looks like here. Turn my multimeter on, and this bulb's getting roughly 12 volts. Let's take a look and see what my second bulb is getting. My second bulb is getting roughly 12 volts, okay? It's kind of a weak power supply. It will start to drop a little bit as I add too much current flow to it, but each leg of the parallel circuit gets full source voltage, okay? It does not have to share voltage with the other loads. So, if one of these bulbs burns out, it will not affect the other bulbs. Now, one thing that's gonna have happen to these bulbs is they're gonna be really, really hot. So I'm gonna grab me a rag. When I pull this bulb out, the other bulb continues to glow. When I put that bulb back in, both bulbs are glowing, okay? So what happens on one leg of a parallel circuit does not necessarily affect the other leg of the parallel circuit, okay? So our laws for parallel circuits. In a parallel circuit, each leg gets its own source voltage. Each leg has its own power and ground. Each leg can work independently of another. So each leg gets the full source voltage. They don't have to share voltage between legs, okay? Amperage in a parallel circuit is going to be a little bit different too. In a series circuit, we had current flow remain constant throughout the circuit, and if we measured it in the beginning or middle or end of the circuit, we saw that current flow was the same. Well, in a parallel circuit, if we measure current flow in any of these legs, what we're gonna see is that current flow in that leg of the parallel circuit is 1.8 ohms. Let's check the other leg of the parallel circuit. The other leg of the parallel circuit. Sorry, just realized I said 1.8 ohms. That was 1.8 amps. Okay. The other leg of the parallel circuit. We hook this one up. It's about 1.8 amps. So if I have 1.8 amps in one leg, 1.8 amps in another leg, that must mean that the current flow coming from my battery has to be almost 4 amps. Okay, so let's check and see what the current flow coming from the battery is. If I take this fuse out right here, it leaves me with a really nice place to measure current flow. I can put one lead in here, one lead in here, and when I do so, my light board should light back up once I make a good connection. And we can see the current flow now is about 3.7 amps, okay? So the amperage in leg 1 plus the amperage in leg 2 equaled the total current that had to leave the battery, okay? Current flow in a parallel circuit is going to be the sum of the current flow in each leg. The more legs we add to a parallel circuit, the more current flow goes up. If current flow goes up, resistance must go down. So if I add a leg to a parallel circuit and current flow goes up because of that new leg, total resistance of a parallel circuit had to go down in order for there to be more current flow. Because remember, current flow and resistance are on opposite ends of the seesaw. So when resistance goes up, current flow goes down. When resistance goes down, current flow goes up. So every time we add a leg to a parallel circuit, current flow increases. If current flow increases, total resistance must decrease. So the law for parallel circuits for resistance is total circuit resistance will always be less than the smallest leg of resistance in the circuit. Okay. Voltage is the same for each leg. Amperage is the sum of all legs added together, and total resistance of a parallel circuit will always be less than the resistance of the smallest leg. Those are our laws for parallel circuits. There's one more law that I haven't mentioned yet, and that is Kirchhoff's current law. And Kirchhoff's current law, kind of like the law for series circuits, Kirchhoff's current law tells us that the current flowing into any junction is the same flowing out of that junction. So if there's 1.8 amps flowing into this junction, there's 1.8 amps flowing out of this junction. So if I measure it on either side, it should be the same. If there's 1.8 amps here, there would be 1.8 amps here. If there's 4 amps coming out of the battery here, then there would have to be 4 amps coming back into the battery over here. So where those branches and legs separate, some current flow goes this way, some current flow goes that way, but the total current flow had to be what left the battery and what comes back to the battery. All right, so one more time. Total resistance is always less than the smallest leg. Total amperage is all the legs added together, and voltage is the same for each leg in a parallel circuit. And Kirchhoff's current law tells us that the current flowing into any junction is the same as current flowing out of that junction. Parallel circuits have their biggest advantage because if something happens to one leg, the other legs will still operate as if they were normal circuits. So we use parallel circuits in automobiles. We don't really use series circuits in automobiles. Parallel circuits allow us to have a circuit on the back of a car for our tail lights. If one tail light blows out, the other tail light still works normally. We would not want to drive a car that if one light went out, all the rest of the lights went out. That could be a very dangerous situation on the road. So all of our circuits on our cars are mostly wired in parallel. You can find a few examples of a series circuit or a series parallel circuit somewhere on the automobile, but most of the things that are wired on our cars are going to be parallel circuits. Thanks for watching the video. See you in the next one.